looked at different types of waves, and now this video is going to be about wave properties. So if I have a wave that looks like this, if this is an actual representation of the wave, so if this is a transverse wave, then I can look at this kind of as a plot where this is my x position in meters, this is my y position in meters. Now, I can label a handful of different things on here, and these are the properties that we're going to be using a lot. But a big thing to recognize, while the y-axis is going to stay the same pretty much always, the x-axis is the thing to pay attention to. When the x-axis is position, like it is right now, we're going to have one set of properties, and then later on, right after this, I'm going to change this x-axis to time, and we're going to have a slightly different set of properties. So just pay attention to what it is we're looking at. This wave has an equilibrium position. That's where the wave would be if you didn't do anything. That's where the string would be if you didn't do anything. And this is that equilibrium position. A different way to think about the equilibrium position is to say that this is the average position of the wave. You spend as much time above it as you do below it. So there's equilibrium. This wave lives between here and here. So it goes up a distance from equilibrium and it goes down a distance from equilibrium. And that's going to be the same value. So these two are the same as each other, and that gets a capital letter A. A is going to be our wave amplitude. We give this as a positive number, but it's the same magnitude above and below equilibrium. Because it's a value that we're measuring on the y-axis, it's going to have units of meters, or whatever the units on your y-axis are. I'm going to leave that one in red, because that one's going to stay the same regardless. I can look right here. Here's part of my wave, here is another corresponding part, and it's the same, right? This is one kind of wave unit. I go from the top to the bottom back to the top. If I look at that piece, I have the same piece repeated over here. I go down and back up. Now I don't have to mark that between a peak and a peak. I can say, between a trough and a trough. That's fine. I can say, well, right here I cross the axis. The only reason that I'm a little bit hesitant to do that is because the next time I cross the axis is here, and that's only half a wave. I've done the up bump, but not the down bump. So if I'm going to mark here, I'm crossing the axis and moving upward. Here's the next time I'm crossing the axis and moving upward. Any of those work. But this thing is, again, on the x-axis, so I'm measuring a length. This is how much length one wave unit takes up, and that gets a Greek letter lambda. Lowercase lambda. And lambda is called a wavelength. It has units of meters, or whatever is on the x-axis. If that's in centimeters, then it has units of centimeters. Those are the properties I can get off of this graph. But I could also plot this a little bit differently. If I have my wave, and I have my string, and I tie a ribbon onto here, that ribbon is going to move up when there's a pulse. That's up. But then, if this is a wave that's going to continue and be fed over and over again instead of just one pulse, then later on, that string is going to be downward pulsing there, and the ribbon's going to move down. So I need a way of expressing that. If I take a set of axes like this, and I try and draw this out, now instead of taking my wave like this, the top graph, I'm saying I'm going to take this wave, which is doing this in this moment. This top graph is frozen in time. This bottom graph, what I'm going to do is now I'm going to look at just the position of that ribbon. So this bottom graph, I'm looking at a frozen location in X anyway. I'm looking at a frozen location and seeing what's happening at that location. Which means now I want to plot this thing not against position, but against time. My y-axis is still going to be y, and my wave is going to look like this. This wave still lives between the positive and negative amplitude because my y-axis hasn't changed. So nothing that I measure on the y-axis should be changing. However, I changed what my x-axis, what my horizontal axis is. It's no longer x, now it's t. Which means if I make a measurement along this axis, kind of the corresponding measurement to what I was doing before, if I make a measurement here, I'm not making a measurement of distance anymore. I'm now making a measurement of time. So this is the amount of time that passes by from when the ribbon is up at its highest point. It's going to go all the way down and come back up to its highest point. This thing gets a capital letter T, and T is called the wave period, or the period of oscillation. It gets units of whatever's on this axis, which in SI units is seconds, but it could be, minutes or milliseconds or something if we're measuring a wave that takes a long time or that's really fast. So then I'm going to put some of these things together. I have these quantities: amplitude, and this is my maximum displacement. I have a wavelength, and I have the period of the wave. Those I'm able to get directly from my graph. I also have a couple of quantities that are going to be calculated quantities. I'm going to have a frequency and that's something I'm going to use quite a bit. Now, the period is the time needed for one oscillation. So this is the time per oscillation, or maybe we can write it this way: seconds per cycle. The frequency is the opposite of this. This is how many cycles we can get in 1 second. So this gets units of 1/seconds, or seconds to the -1. But those are awkward units to write, so we also say hertz. 1 hertz, capital H lowercase z, is 1 inverse second. This is HERTZ. z. So that's frequency. Now if period is seconds per cycle and frequency is cycles per second, then you have probably already figured out the relationship between these, that frequency is just 1 over the period. We're going to have one more number that's calculated. That's kind of an odd one, and it is omega. And we even say omega naught, but let's leave omega. Omega is something called the natural frequency. Which is different than the regular frequency. The natural frequency is saying, I've got this wave, and anytime we're doing a wave, we're looking at like sinusoidal functions, so we've got like a sine cosine type of thing going on. If you plug into your calculator the sine or cosine of a number, sine and cosine are repetitive, and they are repetitive every 2 pi radians, right? Math people really like to use radians. They are repetitive every 2 pi radians. The natural frequency is trying to hit that. Instead of saying cycles per second, it wants radians per second. And if 1 cycle equals 2 pi radians, then our natural frequency is going to be 2 pi times f, which is in radians per second. One last thing. In math, strictly radians are a unitless quantity, which is sort of an odd in-between to hold on to, right? When we need them to be there, we throw in radians, and when we don't need them to be there, radians kind of disappear. So you will sometimes see this written, potentially, as inverse seconds, which is confusing with this seconds. To avoid the confusion, in this course at least, and honestly in a lot of journals, to avoid the confusion you will see regular frequency written out in hertz, and angular frequency or natural frequency written out in radians per second. Strictly speaking, both of them could be written as inverse seconds. You just probably won't see that very often. Hopefully not at all. I'm going to add a side note, and this is something that might be good to have seen, but it's not something that really comes up. Just at some point or other, it might be worth seeing. In the same way that we have these operations that we do with frequency and natural frequency, which are operations of the period, we can do the same with the wavelength. So we have this quantity that we call a wave number. And that's going to be, wave number is just going to be 1 over the wavelength. And then we're going to have a natural wave number, which is just 2 pi times the regular wave number. These are not, again, quantities that you're likely to run into probably ever. But in case you were wondering, well, we do these things to the period, why don't we do anything to the wavelength? We do. It's just, there's not really a huge benefit in having both. So we just stick with the one versus the other. Last piece. So we've got all these quantities, and now we can do a little bit more, because there is a quantity that we haven't really looked at all, and it's a very easy quantity to ask about. If I've got this wave pulse and it's traveling down a line, one question that comes up or should come up is, how fast is this thing moving? What is the actual speed of the wave? And to answer that, I'm going to pull a couple of pieces together. We have this wavelength that's written in meters. We have this frequency that's written in inverse seconds, or the period that's written in seconds. Let's use that one. And a wave speed. Well, if that's going to be some kind of a speed, it should probably be written in meters per second. And it is. We're going to say V is equal to lambda over T. Meters divided by seconds. Because 1 over t is the frequency, we can also write this as lambda times f. It seems like we would just use the period for pretty much everything, but it turns out that a lot of the equations that we work with are direct equations, direct proportionalities when we use frequency. So most of the time when we do waves, we are talking about a wavelength and a frequency, or a wavelength and a natural frequency. The period is easier to see on a graph or on a representation of the wave, but the frequency, if you use the frequency, it means that your equations generally don't have fractions in them, which is kind of a nice deal. So we've got a wave speed, which is in meters per second, a wavelength in meters, and a frequency in hertz. Amplitude is also in meters. Those are the major properties of a wave.